Let's start by recalling the Year 1 version of the binomial theorem. If n is a natural number and we have a plus b in brackets to the power n, we can expand that as n choose 0 times a to the n plus n choose 1 times a to the n minus 1b, all the way up to n choose n b to the power n, where of course n choose k is given by the familiar formula n factorial over k factorial times n minus k factorial. But this doesn't work if n is not a positive integer. So if we consider the following result, which is a generalization of the binomial theorem. So this is really the full binomial theorem, or what's sometimes called Newton's binomial theorem because it's due to Isaac Newton. If we let n be a real number now, any real number, then 1 plus x to the power n is, in fact, sorry, I should have said n is a real number, but n is not a non-negative integer. So let n be a real number and n is not a natural number. Then 1 plus x to the n is given by the formula 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n minus 1, n minus 2 over 3 factorial x cubed plus, and the general term is n minus 1, n minus 2, all the way down to n minus r plus 1 over r factorial x to the r. And this continues forever. So this is an infinite series. It doesn't stop. So you only get a finite binomial expansion when n is a natural number. If n is not a natural number, we instead have this infinite series. And notice this is, although the terms look familiar, the coefficients of the powers of x look familiar to these coefficients here. In fact, they agree when n is a natural number. But the reason we don't write it like this is because this n choose k, these binomial coefficients, are only defined for natural numbers. So this is an infinite series that continues forever. And the proof is quite complicated, again, due to Newton. One proof involves setting up a differential equation, so it's quite complicated. To give you some idea of the level of difficulty, it's one of the optional questions on a further maths differential equations homework. But so we'll skip the proof for now. Okay, so but this is not, the other comment to make about this series is it's not always valid. This is only valid when the modulus of x is less than 1. So this series is only valid if we have something of the form 1 plus x to the n, where n is not a natural number. It's only valid if this number x is between minus 1 and 1. That's what it means for the modulus of x to be less than 1. So let's see an example. So let's take the example expand in ascending powers of x up to and including the term in x cubed, the square root of 1 minus 2x. State the range of values for which the expansion is valid. So we need to expand, well, first of all, the root of 1 minus 2x is not in the correct form just yet. We need something in the form 1 plus x to the power n. It doesn't matter that we have a minus 2x instead of x, because we can just replace x everywhere here in this expansion with minus 2x. But it does matter that it's not yet in the form something to the power n. So first let's write it. It's a square root, so that's to the power a half. So we have 1 minus 2x to the power a half. And now let's apply the formula to expand it. So the first term is 1. And it is really important that we have a 1 here. This is not going to work if you don't have a 1 here. So we'll see later how to deal with that. The next term is nx. N is the power, so that's a half times the x, which is actually for us minus 2x. And then the next term is n times n minus 1, so that's a half times minus a half, over 2 factorial times minus 2x squared. And then the next term is n times n minus 1 times n minus 2, all over 3 factorial times minus 2x cubed, and it continues, but we only need these terms. And now all we have to do is simplify the terms. So that's 1, a half times minus 2 is minus 1, so we get minus x, and then a half times minus a half over 2 is minus an eighth, times minus 2 squared, which is 4, so that's minus a half x squared. And then we have on the top here 3 over 8 over 6, so that's I think 1 over 16 times minus 2 cubed, which is minus 8, so that's going to give us also minus a half, I think, if I've done that right. And it keeps going. So that's the answer. And then we're asked to state the range of values for which the expansion is valid. Now, here we were told that this general expression is valid when the modulus of x is less than 1. But note that we didn't use x, we used minus 2x instead of x. So we don't want the modulus of x to be less than 1. For us, we need the modulus of minus 2x to be less than 1. Can we simplify that any further? Well, we can. The modulus of a negative is the same as the modulus of a positive, so this is the same as the modulus of 2x is less than 1. And then if we divide both sides by 2, we obtain the modulus of x is less than a half. So this is when the expansion is valid. The next part of the question is as follows. By substituting in x equals 0.01, use your expansion to approximate root 2. Well, if x is 0.01, we have root of 1 minus 2 times 0.01, which is root of 0.98, which is the root of 98 over 100, which is the root of 98 over 10, and 98 is 49 times 2, so this is 7/10 of root 2. So note that it isn't enough to just substitute 0.01 straight into our expansion and that be the answer. We need to do something else because that only gives us an approximation to 7/10 of root 2. So using our answer to part A, we have that 7/10 of root 2 is approximately, well, our answer to the previous part was 1 minus x, that's 0.01, minus x squared over 2 minus x cubed over 2. So this is our approximation, and then if you put this into your calculator, you will obtain 0.9899495, I believe. And then to approximate root 2, we need to make it so it's just root 2 on this side. So we can times both sides by 10/7. So root 2 is approximately 10/7 times 0.9899495, which gives us 1.414213571. So this is our approximation, and it continues. But this is our approximation to root 2. In the next example, we're given that in the expansion of 1 plus kx to the power minus 4, the coefficient of x squared is 160. Given that k is negative, find the first three terms of the expansion in ascending powers of x. Okay, well let's just start expanding it. Even though we don't know what k is, we're going to get, the first term is 1, and then the next term is nx, but we have kx in place of x, and our n is minus 4, so we're going to get minus 4 kx. And then the next term is n times n minus 1 over 2 factorial times kx all squared. And we don't need to go any further than this because we're only asked to find the first three terms in this question. So this simplifies to give us 1 minus 4kx, and then this is 20 over 2, so it's 10k squared x squared. And then we're told the coefficient of x squared is 160. So we know 10k squared is 160. And this tells us k squared is 16, so k is plus or minus 4. But k is negative, so we know in fact that k is minus 4. And then if we put this back into the expansion, we get that the first three terms are 1 minus 4k is 16, so we get plus 16x plus 160x squared. And that's the answer. In this example, we want to expand the square root of 1 minus 2x over 1 minus 4x all to the power 4. So we can use the fact that the root of 1 minus 2x over 1 minus 4x to the power 4 we can write as 1 minus 2x to the power half times 1 minus 4x to the power minus 4. So if you have a product or a quotient, you need to somehow write it as the product of two things you can use the binomial theorem to expand. And then notice that both of these functions we expanded in the previous examples. So we found before that 1 minus 2x to the power half was 1 minus x minus a half x squared, and so on. And 1 minus 4x to the minus 4 was 1 plus 16x plus 160x squared, and so on. And then we want to look at how can we make a constant term. The only way when you expand these brackets to make just a number is 1 times 1, which is 1. And then to make x, we can have 1 times 16x and minus x times 1. And then to make x squared, we can have 1 times 160x squared and minus a half x squared times 1, and minus x times 16x, which gives us minus 16x squared. And we're only interested in the first three terms, so we can stop there. And then if we simplify, we've got 1 plus 15x, and then 160 minus 16, that's 144, minus a half, that's 287 over 2, x squared. And that's it. And then we're asked to state the range of values for which the expansion is valid. Well, we had two different expansions we did. So we need to look at when they're both valid, and then think about the values of x that satisfy both of those conditions. So the first expansion, 1 minus 2x to the half, that's valid when the modulus of x is less than a half, and the second expansion is valid when the modulus of x is less than a quarter. So we need both of these to hold. The only way that both of them can hold is if the modulus of x is less than a quarter. So this is the range of values which the expansion is valid.